Okay, let's unpack this. For years, we've seen large language models do amazing things, right? Writing text, coding. But there's this one area, a real peak of mathematical challenge for students before university, where they've typically struggled. That's the International Mathematical Olympiad, the IMO. It's famous for problems that need more than just calculation. They demand deep insight, creativity, and crucially, rigorous proofs. And historically, LLMs haven't been great at that kind of multi-step, complex reasoning. They might do well on benchmarks like GSM-8K or math, maybe through pattern matching. But IMO problems, they're different. They really show the gap, needing abstraction, innovation, things closer to how human experts think. But today we're digging into something fascinating. A recent paper shows Google's Gemini 2.5 Pro having surprising success with the brand new IMO 2025 problems.
Yeah, and what's really interesting, I think, isn't just that the model is powerful, although Gemini 2.5 Pro certainly is. We've seen progress before, maybe with chain of thought prompts. But these Olympiad problems, they remain this huge hurdle. Models would often fall into, logical traps or just lack that creative spark. It really highlights the difference between getting a number right and building a solid logical argument. So this deep dive, it's really about how a very carefully designed self-verification pipeline was the key. That's what let the LLM tackle these problems and, amazingly, solve 5 out of 6.
Right. So our mission here is to pull out the key insights from this research, understand the mechanics, the nuts and bolts of this breakthrough, and explore what it really tells us about where advanced AI reasoning is heading.
IMO problems, they really are a tough benchmark for AI. They demand that deep insight, that ability to connect different mathematical ideas. They're not like some other math tests for AI. These ones really expose the limits, like the tendency to hallucinate or make things up or just use simple shortcuts instead of real understanding. Having wrestled with similar proofs myself, I can tell you they don't give up their secrets easily. These problems are designed to be hard.
So how did they manage it? How did they get Gemini 2.5 Pro to tackle these, well, mathematical fortresses? You mentioned this pipeline.
That's the core of it. The paper lays out this crucial element, a really meticulously built self-verification pipeline. It's not just about the model's power, but how it's guided.
Okay, tell us about that. How does it work?
It's a 6-step process, basically a flow designed to mimic, maybe even improve on how a person might methodically work through such a problem. Step 1 is initial solution generation. The prompt that gets really stressed is that rigor is paramount. Be honest about completeness, it's told. Give a complete, rigorously justified solution. Or, if you can't, give significant partial results you can rigorously prove. All the math needs to be in text format that's standard for math papers, and the output has a clear structure, a summary with the verdict and method sketch, then the detailed solution.
Okay, so it tries to generate a proof, being very careful about rigor from the start. What's step 2?
Step 2 is self-improvement. This tackles a big practical limit for LLMs, the thinking budget. Gemini 2.5 Pro has a maximum budget of 32,768 tokens per thought. Think of it like it's working memory or scratchpad space. For a complex IMO problem, that's often just not enough in one shot. So step 2 basically injects another budget of 32,768 tokens. It lets the model review what it did first, so keep working on it, developing the solution further. They actually saw outputs improve noticeably here, like it got a second chance to think deeper.
So it's like giving it pause to reflect and maybe expand on its initial ideas instead of just one rushed attempt. That makes sense for these kinds of problems. What happens after it's had more time to think?
Then comes step 3, verification. This is where a separate verifier component comes in. Think of it as an expert mathematician, but also a super meticulous grader. Its only job is to find and report all the issues. Really important, it doesn't fix them. It classifies problems into 2 types. Critical errors, these are the big ones. Logical mistakes, factual errors that just break the argument, like saying A implies B when it doesn't. And the other type is justification gaps. These are more like incomplete arguments, maybe a bit hand-wavy. The conclusion might be right, but the steps aren't fully explained. The verifier then spits out a bug report listing all these issues with explanations.
Okay, so a quality control check that pinpoints the problems, like getting reviewer comments on a paper. What's done with that bug report?
That takes us to step 4, which is actually optional, review of the bug report. This step allows for a check on the verifier's report. Sometimes the verifier might make a mistake too, right? So this step lets someone potentially delete reported issues if the verifier got it wrong. It boosts the reliability of the feedback going back to the model.
Okay, so you make sure the feedback is accurate. Then what?
Step 5 is correction or improvement. Now, the original model, the one generating the solution, gets that refined bug report. And its job is to try and fix its own work based on that feedback. address the critical errors, fill in those justification
And
gaps.
it just keeps going. How does it know when the solution is actually good enough?
Good question. That's the final step. 6. Accept or reject. This whole loop verification, review, correction can repeat. Steps 3 to 5 iterate. A solution is only accepted if it passes verification robustly. Specifically, the paper mentions it needs to pass a verifier check 5 times in a row without any issues found. If it keeps having critical errors or major gaps after several tries, the solution gets rejected. It's this systematic, iterative loop that really makes the difference. It's kind of like peer review, but automated and repeated.
Wow, okay, so that iterative process, with the verifier guiding it, that seems key. It helps overcome limits like the thinking budget or just catching those errors that creep into a first draft. That multi-pass approach, reviewing and correcting, sounds like it would make the final output much more reliable. So the big question, did this sophisticated pipeline actually deliver? How did Gemini 2.5 Pro do on these super tough IMO problems?
The results were, frankly, quite impressive. The pipeline managed to generate complete mathematically sound solutions for 5 out of the 6 problems from the IMO 2025 set.
Yeah.
That's a really significant result.
5 out of 6, wow.
And there's a critical detail here. They specifically used the problems from the very latest IMO 2025 competition. These problems had only been released days before they ran the evaluation. This makes it a really clean test. It reduces the worry about data leakage, the model having accidentally seen similar problems during training. It's a strong test of genuine reasoning on unseen challenges.
That's super important for validation, yeah. Making sure it's reasoning, not just recalling something similar. Did it need any help, any hints for these problems?
For some problems, no hints were needed. It generated solutions completely from scratch. For problems 1 and 2, though, they did provide hints. For problem 1, it was a suggestion to use mathematical induction. For problem 2, analytic geometry. But the paper makes it clear these hints mostly just improved efficiency. They didn't seem to unlock a capability the model didn't already have. They found that just running the model for longer, giving it more computational attempts, could likely get the same results without hints. So the core competence was there.
Okay, so the hints helped speed things up, but weren't strictly necessary with enough compute time. Can you give us a flavor of the kinds of problems it solved?
Sure. Problem 1, called sunny lines, was a geometry problem. It involved points and lines in a plane, thinking about configurations. Then problem 3, Banza functions, was number theory. Quite abstract, asking for a specific constant related to a special type of function. The model correctly found the constant was C4. And problem 5, inequality game, was game theory, a 2-player game involving choosing numbers based on sums and squares. The system figured out the exact winning conditions based on a parameter, lambda. It determined Alice wins if lambda is over root 2 over 2, Bazo wins if it's under, and it's a draw if it's equal.
Geometry, number theory, game theory, that's a pretty broad range of mathematical thinking. But you said 5 out of 6. Which one did it fail on and what went wrong?
Right. Despite the overall success, it didn't manage to solve problem 6. This one was a combinatorics problem mixed with some geometry about tiling a large grid, a 2025 by 2025 grid. The model did get partway there. It correctly identified an easy upper limit on the number of tiles needed, 4048. That's a decent start. But its attempt to prove a matching lower bound, which would complete the solution, was based on a fundamentally flawed assumption.
A flawed assumption. What was the error?
The core mistake in its reasoning for problem 6 was this assertion it made. It claimed that any tile used must lie entirely in one of 2 separate regions, either all the cells to the left of the grid's uncovered squares or all the cells to the right. But that's just not correct. A single tile could easily cross columns. It could be left of one row's uncovered square but right of another row's uncovered square. Because that initial claim was wrong, the whole proof built on top of it just fell apart. It couldn't lead to a correct solution. It really shows that even with a strong verification loop, if a core premise is wrong early on, the system can still get stuck down an incorrect path.
Interesting. So even this advanced system isn't foolproof, especially on the trickiest problems where a subtle insight is needed. So, stepping back, what's the main takeaway here? This deep dive certainly shows a big step forward in automated math reasoning, right? Moving beyond just getting answers to building proofs. It seems to show that these powerful models can tackle very hard reasoning tasks, but maybe the strategy and the architecture around them are just as important.
I think that's exactly it. Connecting this to the bigger picture It really emphasizes that even with a very capable base model like Gemini 2.5 Pro, how you design the process, that reasoning pipeline, especially the iterative self-correction and verification, that seems absolutely critical for hitting human expert levels on these really complex multi-step challenges like the IMO problems. It's maybe less about just scaling up the model and more about designing the intelligence, the workflow.
That definitely gives us something to think about. And it leads to a question for you, the listener, to ponder. If this kind of structured, iterative, self-correcting pipeline works so well for math proofs, how might similar approaches transform other fields? Think about areas where complex reasoning and rigorous checking are vital, maybe scientific discovery, legal arguments, complex engineering. Where else could this structured thinking make a difference?